Welcome everyone. I wanted to go over quiz 3 here and we'll probably talk about it in class, but I kind of wanted to build an answer key just so I could start grading, but also kind of think out loud as I answer these to help us hone our test taking strategies here. I don't know if the physics is what's always getting in our way when we sit down and take these quizzes. I'm noticing a lot of mistakes that we wouldn't make in class had we just been pressure off talking about things, maybe not feeling under the time clock or under the gun, so to speak. So we're going to go over this and then obviously do corrections for anything that you missed. Question 1 here, this was pure momentum. Okay, this was all about Unit 3 stuff. Mr. Geidel goes to shovel pile of snow. It takes much force, but the shovel takes a 5-kilogram scoop of snow and it begins to slide forward. Friction is negligible. Geidel has a mass of about 90 kilograms. So considering just the scoop of snow alone, is the momentum of the scoop of snow conserved? Well, the fact that I'm pointing out that I'm only looking at this scoop of snow, that automatically to me calls out system of interest. So I know I am going to use the fact that what counts as my system to answer this. In just the scoop of snow alone, is momentum conserved? Well, we could talk about how momentum initial doesn't equal momentum final because it goes from rest to some speed. Okay, no, it's not. Okay, but we said momentum is always conserved. Well, not really. We said momentum is always conserved unless there is an outside force. That's outside force, which causes an impulse. Okay, so if I were to calculate, force times the time frame, I could get an impulse, and that was the impulse received by the scoop of snow alone. All right, 1B. Okay, considering Mr. Geidel and the scoop of snow as one system, right there, language in the question calling out, hey, the system you consider matters. The system you consider matters. Okay, so here, if the Geidel, and a lot of questions in the class, does the shovel not count as? But yes, the shovel's part of the system. Okay, Geidel pushes on the shovel pushes on the snow pushes back on the shovel pushes back on Geidel. It's all internal forces. Things can still move, things can still accelerate. Okay, but the forces on the system as a whole cancel out. Okay, so momentum is conserved. Okay, if we looked at the center of mass of this system, we'd find that it is not accelerating. Okay, there's no external forces on the entire system. All right. It takes 500 milliseconds for the scoop of snow to go from rest to a speed of 0.8 meters per second forward. What is the average force Geidel applies to the scoop of snow during this time? Okay. Remember, we get to redraw our system of interest to suit our needs, kind of like we pick a coordinate system to suit our needs. Right? We have a time frame. We're looking for a force. Okay, we have information about mass, and here we also have a change of velocity. Okay, let's consider just the scoop of snow because we know that the impulse is the force times the time, which is great. I have a time, I'm solving for a force, right? And I know that an impulse is also a change in momentum, which in this course is pretty much going to be a result of the change in velocity. Okay, so this is our what we call the impulse momentum formula. And we're going to solve it for the force, which we even recognize this version of it too, hopefully, as the original Newton's second law, or more closely like the original Newton's second law. Okay, so it's the mass of the snow is 5 kilograms. Oh, I don't know if that's reasonable for a scoop of snow or not. It felt like it that day. We got a snow day. Mass times the change, it went from rest to 0.8 meters per second, okay, over the course of 500 milliseconds. Okay. Clack it up. Fancy new batteries in my... Can you even see that? I don't think you can see that still. Oh yeah, there you go, there you go. Milli is 1/1000th. Okay. 8 newtons. Okay. Kilogram meters per second squared. Okay. 8 newtons on average over that time. D. What force does the scoop of snow apply to Mr. Geidel during this time? Show your work or justify with logic. Hey, we went from show your work to show your work or justify. Right there, that's a little in-question clue that maybe you can use logic to do this. Well, okay, if Geidel pushes on the snow at 8 newtons, the snow pushes back with 8 newtons. Newton's third law. Action. Reaction. Pair. Okay. 1E. Since the icy conditions made friction negligible, Geidel begins to slide as a result of the collision with the scoop of snow. And even in that question, too, if you didn't know to invoke momentum at this point, hopefully you did as I suggested and read through the quiz before starting, you see this wording here, and it's a hint. It's telling you to treat this like a collision, which momentum is the tool we use to do collisions and explosions. So as a result of this collision with the scoop, what speed and direction does Mr. Geidel slide? Okay, show your work. Right, I know that the change in momentum, right, or rather the momentum before the collision is the momentum after the collision. Okay? So if I know the gain, right, which there was no momentum before, which means there's no momentum after. So Geidel's momentum plus the snow's momentum must add up to 0. Okay? When we consider, see now we're considering the whole, both of them again together again. Why? Because it's convenient. We know that the two of them had no momentum after, thus one's after the collision, right? And this is why the shovel wasn't explicitly worded in the question, right? The shovel goes forward as the arms, Mr. Geidel sliding backwards. Okay, whatever momentum the snow carried off forward is the momentum Geidel has going backwards. Okay? So that kind of gives us... And, you know, one of them is going to pick up a minus sign. And that's just to remind us that they're in opposite directions, but we knew that. And if we forgot to make it explicit with a minus sign, we could tack it onto our answer too. Right? Did we solve for this before? We know they have 8 newtons for us, but no. But we know the mass times the change times the velocity. Right, whatever momentum the snow has is what Geidel has. So let's find the momentum of the snow, because that's the same momentum Geidel has. Okay, what was it? 5 kilograms. Right, the snow's moving at 0.8. Got ahead of myself. I think it should be 40, right? 5. So that's how much momentum the snow had going forward, which means that's how much I had after. Actually picks up a negative, but that's okay. Equals Geidel's mass times Geidel's velocity. Okay, 4 over my 90 kilograms. Okay, which is what? 0.04. Right, kilograms cancel. Meters per second. And then we want to include the direction as speed and direction, so we want the full velocity. If you look in the question, okay, that point, that 0.8 meters per second was what we're calling forward. I don't know which way forward is, north, to the right, down the driveway, whatever. That one was forward, so this one is backwards. Good. Right, and that's question 1. Okay, all momentum there. The other question did use some of the other units as promised and as practiced in class. Okay. 800-gram model rocket has a solid fuel engine that burns for 1.4 seconds with an average thrust force of 12 newtons. It's launched from rest, straight upwards. Air friction and mass of the engine are negligible. Okay, A, what impulse does the engine give the rocket? Okay, so the question is, what impulse? So your answer is impulse is. Okay. We have a formula, and hopefully you put it on a little cheat sheet that I suggested you make, and hopefully you've just been building on from the prior quizzes. Okay, we have 2 ways to do impulse. It is a change in momentum. Okay, impulse is also force over time, over a period of time, force times time. Okay, I have a time frame, 1.4 seconds, and I have an average thrust, 12 newtons. So let's use this version of it. If I have 12 newtons going for 1.4 seconds, I get an impulse of come on, autofocus, 16.8 newton seconds. Right, that's the kick given to the rocket by the engine. B, what is the velocity of the rocket when the engine burns out? We had a question just like this on Unit 2 quiz. Okay, so this was a chance kind of for redemption here, because I know that quiz lumped up some of us and we wanted to get it back good. So this was our chance. Okay, we have a force acting over a little bit of time here. I'm looking for things like a velocity at the end of a time period, velocity final, and time. There were kinematics variables. Okay, let's set up a kinematics chart. Right, the rocket's shot straight upwards, so I'm going to make a chart for the y direction. Okay. Okay. I want to know the final velocity when the engine burns out. So my time frame here is from launch to engine out. Is this coming back to you now? Okay, before the engine starts, the velocity is 0. It even says in the question that it's launched from rest straight forward, or straight upward, sorry. Okay, I'm looking for the final velocity. I don't know anything about the displacement. I know during the kind of powered stage of this, I have 2 forces at play here. I have a thrust, force of thrust, and I have the rocket's weight going down. Okay. I noticed some people putting in, they used Newton's second law to find an acceleration using 12 newtons. That's not the only force at play here. All right, the net force in the y direction is ma, right, and that is the acceleration that's going to go in there, but there's 2 forces. Right, I have 12 newtons going up, and I have its weight going down. Okay, I have 0.8. If I have 0.8 kilograms times acceleration due to gravity, right, there's an 8 Newton force of force of gravity downwards. Okay, so it is the difference, ma equals the net force of 4 newtons upwards. Okay, so the acceleration there Just like, I mean, it was a different value, but and that makes sense, right? It's accelerating upwards. There's a rocket burning upwards. Don't plug in negative 10 meters per second squared there. That's a free fall. This thing is not in free fall if there's an engine burning. Right? And that's why it's very important to make clear the motion you're analyzing there. This is powered flight. Hey, we even know how long the engine burns for, right? From launch to engine out is 1.4 seconds. I've got 3 kinematics variables. I can solve for a 4th. Let's see, out of my 4 equations that hopefully are on your cheat sheet, this would be one of them. Okay. If I accelerate for 5 meters per second squared for 1.4 seconds, I end up at a velocity of 7 meters per second. And it's positive, so it's in the same direction as the acceleration, which is upwards. So that's how fast, that is the velocity of the engine when it goes out. What is the average acceleration of the rocket while the engine burns? I actually, we did that. I should have asked those in the opposite order. (2D), how high is the rocket when the engine goes out? Okay, when the engine goes out. When the engine goes out. We're using the same kinematics chart. Okay, how high is it when the engine goes out? Okay, now we have, that's our 7. And now I want the displacement during that time. Okay, I liked, and I went over this in class, we worked hard to get that 7 meters per second. Okay, we can use that, but I like to use the stuff given to me in the problem. I guess we solved for the 5 meters per second squared too, so maybe it's just OCD, but really the options open up to you because now you got 4 variables to find a 5th. Let's see what equation would do this. If I have initial velocity, acceleration, so is that our delta y equals VIT plus 1/2 AT squared, and that's 0. .9 meters. The rocket in the Unit 2 example was heavier. It had a larger mass, if I'm not mistaken, and the impulse, we weren't talking in terms of impulse, but it had a much stronger engine. And so when I saw people questioning themselves just because they didn't think this answer was high enough. I mean, we accelerated from 5 meters per second squared for 1.4 seconds. Also, and the engine burned much longer in that problem. I think it's great for people to be critical. Sorry, the earlier last time had a smaller mass. I think it's great that people are looking at their answers and seeing if it makes sense. But, this is about 5 meters. It's like 20 feet. It's 2 stories for almost a kilogram. I don't know, maybe, I hope my numbers didn't throw you off there. Okay, we've done everything right so far, and if not, if anyone catches anything by any means, whether it's in the question or in my kind of analysis here, put it in the comments, because I'd love to, no sense being wrong if we can be right. So, as far as, and this is just when the engine goes out, we're still heading upwards at 7 meters per second at this point. Okay, so I think that's great that you're self-checking the answers to see if they make sense, but I guess model rockets can go much higher than 20-ish feet, but they don't have to. This one didn't. If the numbers are if we did the right things with them. So what is the maximum height above the ground that the rocket reaches? So in 2E, we do need another chart because now we want it to end at the peak. Okay, how high is the rocket? It's going to be the y direction. Okay, and I want this to end. I want my section of motion to end at the peak. Okay, we still have the same kinematics variables. Okay. Can I put from launch to peak? Because that would be great, right? That would give me the maximum height above the ground. Okay, there's a problem though with that, and it's the same problem we faced in when we did this before for the forces quiz. Okay, I have an engine burns, the engine cuts out, I go up, and then I fall down. Okay, and I want to know in this part of the question, I'm looking for the maximum height. Okay. There's a problem with going from launch to peak here, and first of all, or maybe it might be the only problem actually, is that the acceleration isn't the same during that. Okay, I can only put one value for acceleration here. Do I put the acceleration while the engine's burning, or do I put the acceleration due to gravity? When that engine cuts out, this becomes a free fall problem. And really, I can't put both. I have to do one or the other. Okay, I happen to know a little bit of information about the rocket at this point. Okay? The final velocity when the engine cuts out is 7 meters per second. If I go from engine out to peak, I know my velocity at that moment. I know the velocity at the peak of a trajectory. Okay, that displacement isn't the full height, but we also know how high off the ground this was. It was our 4.9 meters. Okay. So just like in the forces quiz, okay, we're going to use this second bit of motion here. We're looking at this right now, where gravity is the only influence, ignoring friction, and the engine's off, all that fun stuff. Okay, but I've got 3 kinematics variables I can solve for a fourth. There's only one of the 4 equations that don't include time. It's that one. That's 0. I'm going to subtract that over. And I'm going to divide 2a over. Alright, and plug in what we got. So I start off at 7 meters per second upward. Oh, that's a sloppy delta. Alright, let's see. The negatives. A negative divided by negative is positive, so I'm just going to ignore that. 49 divided by 2 divided by 10. Alright, 2.45. So it's going to travel another 2.45 meters before it comes to the peak. Okay, is this the highest, most screaming rocket in the world? No. Okay, but did we do the physics right? Yes. Are we going to just run with it? Yes. And I mean, we're still here. Let's see. Our total height then is the 4.9 meters of powered flight plus the 2.45 meters. We kept going. For a grand total of 7.35 meters. Which is about, I guess it's a little over 20 feet. Okay, not the most screaming rocket. We wouldn't get it into the SpaceX fleet, but we got to practice some kinematics and forces. So what gives, right, is a momentum quiz? Well, the rocket's parachute fails to open and it falls to the ground. Ignore air resistance. With what speed is it moving as it comes in contact with the ground? Okay, so as it comes in contact with the ground, we're talking about this moment right here. And we want to know its velocity right here. Maybe you can see where we're going with this. Okay, well, we're looking for a velocity, which is a kinematics variable. Okay, and we know a little bit about the fall, right? We know it's not moving at all here, and we know the distance it falls, and we know it's accelerating due to gravity. So this last little bit is a little more kinematics. Okay, and this is going to be from peak to ground contact. Starts off at the peak of 0 meters per second. We want to know its speed as it contacts the ground. We know it's going to be negative, right? It's going to be 7.35 meters lower than it starts. Okay, and remember, displacement is always final minus initial. I have a final height of 0. Minus my initial height of h, or 7.35. So that's where I pick up that negative, right? It's always final, except not velocity final. Okay, it's position final minus position initial. Displacement is a change of position, and change is always final minus initial. So that's where we pick up that negative from, at least in this coordinate system. I'm accelerating downwards, and here's another little self-check, right? The acceleration is down. The displacement is down. They better have the same sign. Okay. Again, there's only one of the 4 equations that don't involve time. If you've ever wondered why or how I've memorized these, it's because you use them over and over and over and over. Okay. This time this guy's 0. Right. And this is a form that you've probably become familiar with also. Alright, a negative times a negative is a positive. So it's 2 times 10 times 7.35. Right. It's going about 12.12 meters per second. Forgive my lack of interest of significant figures. I promise when I do real science for myself, I do pay attention to sig figs. Okay. Alright, so that's how fast it's moving. When we enter this collision problem, 2g, the ground applies an average force of 1 times 10 to the 4th newtons while the rocket is brought to rest. How long does the collision? If you didn't know to use momentum here, it tells you right there, telling us it's a collision. How long does the collision with the ground take place? I have a force. I'm looking for a time frame. Right, and you can even hear it. All right, I'm moving at 12 meters per second, and I'm brought to rest. It's a change in speed. It's a change in momentum. This is impulse momentum again. So I know the impulse that brings the rocket to rest is equal to its change in momentum. Right, and I'm looking for a time frame this time. The rocket is, it's 800 grams, right? Yep. All right, change in velocity is, right, velocity final minus initial. A change of 12 point. Okay. And actually, just a little note here. I lose half a point. Okay, I know whenever you do a square root, right, there's always a plus or minus. Okay, and here, knowing that we're traveling downwards, we're going to select the negative one to give our vector direction. Minus half a point for Geidel. Okay, so now here, when I do my change in velocity, it's final minus initial. All right, I end up at 0. So I'm going to do minus negative 12. Right, so I'm doing minus a negative. That's how I get back to a positive here. If I didn't catch that, and then when I ended up with a negative time, if I didn't catch it here, I would have caught it there, pinky promise. Okay. My force, which is upwards, the ground pushes on the rocket upwards, so that is a positive force. Forces are in newtons. Alright, so I got 0.8 times my negative of a negative, 12.12, and then I'm going to divide by 1 times 10 to the 4th newtons. This is 9.69 times 10 to the 4th. Sorry, 10 to the negative 4th. It's very different. Seconds. Okay? If I make the coefficient 10 times bigger, to keep an equal number, I make this, if I make this 10 times smaller, I make that 10 times bigger to keep my same answer. I do that, which I guess I could do. 969. We didn't talk about this prefix, but microseconds. Okay, but you'll find that is the same answer. Okay, 0.9 milliseconds. Where we'll do 69. 0.9 milliseconds is also the same answer there. So some fun with metric prefixes there. Okay, you could do the scientific notation one. That's fine. All right, let's bring it on home. Okay, pretend the rocket was carrying an egg, and that egg is in a special container designed to resist crashes. What average force does the 50-gram egg receive if the special container allows the egg to come to rest over the course of 8 milliseconds? Okay, so I'm moving. The whole thing is still moving. Okay, so I'm still going from 12 meters per second to 0, 12 meters per second downward to 0. But now it's over 8 milliseconds instead of 0.9 milliseconds. And this is just the egg here that's happening. Okay, so I'm looking for a force, okay, that happens over a longer period of time. This is another impulse momentum. It's going to be the egg's change in momentum. Okay. Now, does the egg have the same change in momentum? Because a lot of people here, I didn't get this question explicitly, but it was, do I plug in the rocket's mass or the egg's mass? Okay. Well, if I plugged in the rocket's mass, the whole system is moving at 12 meters per second, right? And the whole thing comes to rest. Okay. If I plugged in the rocket's mass here, I'm going to find that they both receive the same impulse. Okay. If you had a seatbelt and an airbag on and you received the same impulse that you would receive without it, it's not a very good seatbelt or airbag, right? That's the whole point of these things, is to reduce the impulse that's on you. Okay? And they usually work by, as you can probably tell on this, by extending the time period that this happens, which lowers the force. Okay, but I'm going to go ahead and I'm going to plug in the mass of the egg here. And this is a question that came up in class, and if anyone has any insight on it, I'm all into that. But, kind of the question we were grappling with is, if I'm walking down the street, okay, I have, Mr. Geidel has a certain momentum. Does my arm have the same momentum? It has less mass than me, but it's part of this whole system. Okay, so how would you grapple with that? Does a piece of a system have the same momentum as the whole system? Okay. I don't want us to get bogged down in all that. I know I have a 50-gram egg, that's moving at 12 meters per second. It goes to 0 meters per second in 8 milliseconds. All right, so I'm looking at the impulse on the egg. Okay, I want to know what the force on the egg is. So I'm going to plug in 50 grams for this. Okay? I want to know what the force is. So 50 grams is 0.05 kilograms. 1, 2, 3 would be 50. Okay, my chain, I'm minusing a negative again. And this 8 milliseconds. .75 newtons. Okay, much less than the 10,000 newtons that the whole rocket received there. Okay. So here you go. You can use this to help you do corrections here. Okay. And if we have any more, I'd love to talk more about whether you'd use the mag, because it sounded like people were wanting to use the mass of the rocket because it's all one system, all one mass. But the rocket is the rocket came to rest much quicker. The rocket received a much bigger impulse. The rocket gets smushed to bits. The rocket's not in a special container designed to crash. I don't think we used the rocket's mass here. And again, any further input to help me out with that, I am all ears. Okay, so that's quiz 3 there. Write it up, do corrections, let me know if you need help, and when we do, Unit 4 is going to be energy. That'll take us to the semester, that'll take us to the end here, and physics is highly cumulative, so even when we do this energy quiz, which I think you'll enjoy energy, it rules out a lot of the details, much like momentum, right? There wasn't as much we had to keep track of. Students usually enjoy it, but when we sit down to take that Unit 4 quiz, momentum's fair game, kinematics are fair game, forces are fair game. So make sure you're keeping up on all of it. All right? Let me put your questions in Google Classroom, email me, talk to me in class, all that fun stuff, office hours, you know the drill. Okay? I'll talk to y'all soon. Thank you.